is this really possible? If we're able to do this, then the law of conservation of energy has been cemented. So in higher dimensions, a force vector dotted with a displacement vector from point 1 to point 2, can we express that as a change in the potential function? There's a question mark here. If you're able to do that, then we have cemented everything. Now, in general, as I said, this cannot be done. Not every force dotted with a displacement vector will give you a change in the potential function. You are going to see special cases where this can be done. Now, therefore, in 3D space, let's call this our z-axis, let's call this y, then call this x. So every scenario of a force system can be expressed in 2D. We can cut a plane through every force that moves an object from a point 1 to a point 2. If you cut the plane through it, that one will lie in the xy plane. So what I mean is, in the xy plane, you have an object located at this point. And let's call this position x1, y1. Now, this is a vector. We call it r1. Then let's just say a force moves an object from x1, y1 to another location here, x2, y2. And that 2 is a vector. Let's call it a vector r2. It has an x component and a y component. So at every point on the trajectory in the xy plane, now the force could be pointed anywhere. And let's define a minute displacement dr on the trajectory, and that too is a vector. So it is this force dotted with this dr from r1 to r2 that we have expressed here. And we are asking, can we write this as a change in the potential function? And we said in general, no, you cannot do it. But in special cases, we can do it. Now in 1D, this potential function was actually an area function. So this integral in 1D was calculating an area under a function. But in 2D, what is it actually doing? What is this integral tracking? Is it also tracking an area? And the answer is no, it isn't. Now, this is where we are going to introduce another function that we call a height function. So in all this problem, at a location x1, y1, now in the 3D space, there is a height function. That is, let's say this is your roof. At location x1, y1, there is a height you can trace to this roof. So it's like your room, your floor, at any point on your floor, you can trace a height to the roof. If you move to a second location, the height you get may be different from the first one. That is the case we are solving here. So let's call this height function u. So at this point, we have this height function as u of x1, y1. So tracking this point to the height, this is what we got. Then at a location x2, y2, we can also hit the roof, and the height it gives us will be a function that depends on x2 and y2. So let's just call it u of x2, y2. This is a height function, which is different from a force function or a displacement function. So we are going to study this height function into detail. Maybe it could help us to express this integral as a change in the potential function. So let's draw another Cartesian plane in 3D. So we have our x, we have our y, we have our x, we have our y, then we have our z. And the reason why we choose XYZ is such that we have something we call cross product, which we'll be talking about in few moments. So XY, S cross Y will give you the Z axis. That was just by the way. So at a location X1, Y1, you have a height function. So you track this and it hits this roof. At this point, we call it U of X1, Y1. And then let's just say you have another location and you track it to the height or the roof. You have U of X2, Y2. That is, this is X2 and then Y2. So at any location in the XY plane, you have a different height. That's what we are studying for now. Now, if these 2 points are very close, that is, if you draw another Cartesian plane, we have X, we have Y, we have X, then we have Z. Now, if these 2 points are very close to each other, now let's just say, let's call this XY, simplistically as XY, and then call this, so we move to a different location, very close to that one. Let's call it X plus delta X. So Y plus delta Y. So we move in such a way that we add a minute change in X and a minute change in Y. Okay. Now, each of these points, of course, hits different height. So we call this U of XY, and then we call this U of X plus delta X, comma Y plus delta Y. Okay. So this is a different height from this. So we ask ourselves, what is the change in the height? That is, there is a change in height here, delta U. How much does the height change as you move from XY to X plus delta X, Y plus delta Y? So we seek to find how much the height changes as we move from XY to this location. So delta U, which is a change in the height function, is equal to, now U at the location S plus delta X, Y plus delta Y, minus U at the location X, Y. That is the change in the height, delta U. Now, let's introduce an intermediate point. Let's just say we move only in Y, keeping X a constant, then we come to this location. We just introduce this mathematical location, which is a constant X, comma, Y plus delta Y. So keeping X constant, moving in Y, you change your Y, but your X is a constant. So this is an intermediate point. So this point minus that point is equal to this point minus that plus this point minus that. We introduce this intermediate point so that we can express this change in calculus terms. So delta U is equal to, now this is the same as U of X plus delta X, comma Y plus delta Y, minus U at this location X, comma Y plus delta Y. So that is this point minus that point, plus this point minus that. So we have U, repeating this one, X, comma Y plus delta Y, minus U of XY. In fact, this whole term is the same as the first term. All that we did was to introduce an intermediate point, U of X, Y plus delta Y. So this is negative that, this is plus that. So this and that cancels. they cancel out, bringing this one to the original we have on top there. So if you ask why we introduce this intermediate point, it's just to express it in calculus terms. Okay, so delta u, the change in the height function, is going to be equal to, now if we look through, with this change, we have x plus delta x, then we have x. X is changing, but here we have y plus delta y plus delta y is not changing. So this difference is such that x changes, keeping y a constant. Now we call this a partial derivative. So this is a change in u with respect to the one that is changing, which is with respect to x. So the partial derivative of u with respect to x, because as we can see here, x changes from x to s plus delta x, keeping y a constant. So we call it a partial derivative. Now, this is a change in u with respect to x times delta x. All that we are trying to find is a delta u. So to restore everything back to delta u, you need to multiply this by delta x. So the partial derivative of u with respect to dx times delta x. So then everything is restored to a change in the height. Where did we compute this derivative, partial derivative of u with respect to x? We computed this, so that is u of x plus delta x, y plus delta y, minus u of xy, minus u of x, y plus delta y. So it is this point minus that point. We computed this derivative at this point. So let's embellish this. Let's be explicit that this derivative, partial derivative of u with respect to x, was computed at this location, x, y plus delta y. I'll tell you why that is important to introduce. So times delta x. Then, so we are done with this first two. Secondly, we have u of x, y plus delta y minus u of xy. Over here, let's see what is changing. X is constant, so we have here x, another x, no change. But we have here y plus delta y, then we have y. So this is a partial derivative of the height function with respect to the one that is changing, which is y. And we compute this derivative. So this is this minus that at this location xy, x comma y, times the one that is changing, delta y. See? This is very important. So in the three-dimensional space, if you are located in a two-dimensional plane, you move from location xy to a location x plus a little change in x, comma y plus a little change in y. Now there is a height function associated with each point that we call u of xy. So at this location you have this height function, and at this location you have this height function, and we seek to see how the height function changes. Delta u. Delta u can be expressed as the height at this location minus the height here. That is when you move from this location to that location. That is the first point. Then we can introduce an intermediate point, x comma y plus delta y. So you move at a constant x by changing your y position. And we introduce this intermediate point to express everything in calculus terms. So the intermediate is this negative and then this positive. They cancel out, restoring everything to original. But we still need them. So the difference here is a partial derivative of the function u with respect to x, or x is the one changing here. Okay, and we computed this derivative at the location x comma y plus delta y, because that is what we have here. Plus this difference will give us a partial derivative of u with respect to y, and we computed this derivative at xy, because that's what we have here, times delta y. So that is delta u, a the partial derivative of u with respect to x times delta x computed at this point, at this location, x y plus delta y, plus the partial derivative with respect to y times delta y computed at this point, xy. Okay. And the problem with this change in u is the fact that the two derivatives are computed at different places. One is computed here, one is also computed at xy. We need to compute the derivatives at just one point, so that if you have that partial derivative, you slot in that point, you get your value. Now, therefore, we need to express this derivative, du, partial derivative of u with respect to x, computed at x y plus delta y. We need to compute it at this point xy. How do we do that? If we compute it at xy, then that means that slope is also changing. What I mean by that is this partial derivative was computed here. If you want to shift that derivative to a point xy, then you need to compute the change in that slope. So as you move from xy to sy plus delta y, that slope will also change. So there will be a second derivative. So delta u, what I mean is equal to, now this partial derivative, that is with respect to x. Now this time round, we are shifting the computation from xy plus delta y to xy, so that there will be a uniformity in the computation, times delta x. But as we shift the derivative from this point to that point, we need to add the change in the slope itself. So that will be a partial derivative, that is the square u dy dx. Why the square u dy dx? It means that this derivative is changing. So we shifted it from here to that point. If you want to restore it back to this point, then the slope that you have computed at xy will change as you move from xy to xy plus delta y. And moving like so, it is y that is changing. So you take the y derivative of this slope. That's what you add to the whole of this. So partial derivative of u with respect to x computed at xy. It was originally computed at xy plus delta y, but we want to compute it at xy. So we need to add the change in the slope itself as y changes. That's why we have the square u dy dx. And that dy dx means y changes as the slope also changes. Plus, so we are done with this one. So it is this one we have expressed as that. So we add the partial derivative of the function with respect to y computed at xy. So now we get both of them computed at xy times delta y. So to rearrange, we have delta u to be equal to the partial derivative of the height function with respect to x computed at xy times delta x, plus the partial derivative of the function with respect to y computed at xy2. So the two of them are computed at xy now, times delta y. Then we need to add the change of this slope with respect to y, because we have shifted its computation from this point to that point. So we add the y derivative of this slope du dx. Now this can be written in two ways. The first way is this one, and the second way is what I wrote over here. And this is a final formula for the change in the height function. It is a partial derivative of the height function with respect to x computed at xy times delta x, plus the partial derivative of the function with respect to y computed at xy2 times delta y, plus the partial derivative with respect to y of this slope. We introduce the second derivative because we need to shift this derivative to xy2. That's how the height function changes. So finally, delta u is equal to the partial derivative of the height function with respect to x computed at xy. Let's omit that. Now we know it is computed at xy, so times delta x plus the partial derivative of the height function with respect to y times delta y plus the y derivative of this slope. So the dy of du dx. This will be useful in the law of conservation of energy in higher dimensions. So this is how physicists stumble upon partial derivatives, which is really important. Now, there is something we need to introduce. So the partial derivative of this slope with respect to y. Now, to restore everything to delta u, we need to multiply this by delta y, delta x. So delta y, delta x. That is the last thing we need to introduce. But we need to also introduce it here. So let's put in mind this is times delta y, delta x. And we do that to restore this back to delta u. If there's a change in u, and the bottom we have dy dx, we need to multiply by delta y, delta x. So there will be a cancellation and restoration over there. Okay. So it turns out that delta y, delta x, this is an infinitesimal displacement in y times another infinitesimal displacement in x. An infinitesimal value times another infinitesimal value. That will be very minute and insignificant. So this quantity, which we call the cross derivative. Now let me explain why we call this a cross derivative. We call it so because now we got this partial derivative with respect to y of the slope du dx because we introduced an intermediate point here where x was a constant and we moved in the y direction. We could have also introduced it here, the intermediate point here, where y would have been a constant, but we move in x. So this is an x-axis. So as we move the intermediate point from this point to that point, here x changes, but y is kept at a constant. So if we introduce the intermediate point here, this quantity will simply change to, so this is equal to the partial derivative, this time round with respect to x. Or if you introduce the intermediate here, it is x that changes, of du dy, of course, times delta x times delta y. So these two derivatives are called cross derivatives and they are equal depending on where you introduce your intermediate point. So the change in the height function is equal to partial derivative of the height function with respect to x times delta x plus partial derivative of the height function with respect to y times delta y. Case closed. Why case closed? Because we are omitting this parameter in the sense that delta y, delta x are two infinitesimals, which will give you an insignificant value. So this is enough to be the change in the height function. But we get another important idea here, that for height function in 3D space, if you want to find the change in that height function, there is something we call cross derivatives, and they are equal. In other words, the y derivative of the change in the height function with respect to x is equal to the x derivative of the change in the height function with respect to y. Let's keep this idea too, which will be a cornerstone in our next episode, cementing the idea of the law of conservation of energy. We keep this important equation, we keep this one too for the next episode. Stay tuned, subscribe to my channel for Proof Advanced Physics, share, comment, and like my videos. In the last episode, we are discussing how we can express the integral of a force vector dot dr from r1 to r2 as maybe u of r1 minus u of r2. So then we generalize the whole conservation formula. That's what gave us the idea of a height function in the xyz plane. space. Stay tuned.